All right, welcome back, class, to a new week of 220A. We were on a roller coaster, bearing down on a theory of phase transitions, and we've made important headway there last week by introducing two canonical models and a couple important concepts. Conceptually, we've discussed ideas of universality and symmetry, and on the model front, we've introduced both the lattice gas and the Ising model, two models that will concern our attention for the next couple weeks. So today, after we review some of those basic notions, reaffirm the equivalence between the Ising model and the lattice gas, so they are in fact the same model, we will actually solve the Ising model under a specific instance of it existing in one dimension, where we'll find something kind of interesting regarding its phase behavior, something I alluded to in the live session on Thursday. Okay, so let's go ahead and begin. So within our discussion of phase transitions, we've introduced a quantitative measure of universality. And that is that if we are to look at specific properties of systems near their critical temperature, that we find universal critical behavior as quantified through so-called critical exponents. So let's review that. So critical exponents quantify universal behavior near the critical point. For example, we've introduced a few. If I was to look at the density of a liquid relative to its critical density near the critical temperature, I would find a power law behavior with an exponent beta, which turns out to be quantitatively close to 0.32. If I was to measure the heat capacity close to the critical point of that same fluid or any other fluid undergoing a liquid vapor phase transition, I would find another power law behavior with a different exponent, so-called alpha, which is pretty small, 0.11. And for a liquid vapor transition, I could alternatively measure the susceptibility, how the order parameter, in this case the density, varies with some conjugate field, in this case pressure, at fixed temperature. This too would vary as a power law relative to the critical temperature with an exponent gamma, turns out to be 1.2. There are an analogous and quantifiably identical set of exponents for other transitions, like demixing transitions, where it's not the density that you measure relative to a critical value, but the composition. Similarly, the same set of exponents also describes simple magnets, where the susceptibility is not how the density changes with pressure, but rather how the magnetic moment varies with applied magnetic field. Nevertheless, such a susceptibility in a simple magnet would have a susceptibility that goes like a power law with that same gamma exponent. Now this observation, this empirical observation that was initially made, unifying this somewhat disparate set of phenomena, motivates an approach to understanding this sort of phenomena which rely on simple models that maybe don't need all of the molecular detail in order to get the basic physics right. Indeed, the fact that water and methanol and argon liquid vapor transitions all behave in the same way suggests that maybe very little detail is really needed in order to uncover why they all act in the same way. So we've introduced a couple simple models. In the context of the liquid vapor transition, we've introduced the so-called lattice gas. If I was going to look at a snapshot of the lattice gas, this would be some lattice. So we've gridded up space. In some of the cells, I would find particles. In others, they would be empty. So one configuration might look like this, in which case this cell empty would be labeled with an indicator function n for that cell I, which was 0, while that cell there, which is filled, would have an associated indicator function, which was 1. The simplest energy we could imagine writing down for such an interacting lattice gas would say that nearest neighbor cells with which both are filled, so both have particles, interact, and they interact with some scale epsilon. It is attractive, returns minus epsilon of energy only if Ni and Nj are both 1, so both filled. And I can imagine that those interactions are short range, so that that sum contains only nearest neighbor interactions. This should be compared to our simple model for a magnet, so-called Ising model, which also lives on a lattice. But in that lattice, there are spins that either point up or down. Each one of those spins are denoted with a spin variable s, which reflect that up-down possibility. So it can be plus or minus 1. The energy function for the Ising model imagines that those spins interact with some exchange coupling J, which is short range and asks for both spins being aligned to return that positive or attractive energy. And in principle, one could apply an external field to modulate the values of those spins, where that H is the value of the external field. Now, in the appropriate ensemble, so for the lattice gas, the grand canonical ensemble, which of course biases configurations based on both their energy as well as the total particle number. And for the Ising model, the canonical ensemble, we noted last class that in those appropriate ensembles, where I recognize that the lattice gas, the particle number can fluctuate, in both the temperature is fixed, we noted that those two partition functions look awfully similar. And in fact, we proved that those models are equivalent to each other. So simple models motivated through different physical means in their simple forms are exactly the same model, can be rewritten in terms of the other variables, of the others variables. We'll go back through that again today just to demonstrate that and remind you of the symmetry of the lattice gas, which is not otherwise easy to discern before we go on to talk about trying to actually solve one of these models. But before I want to go there, I want to draw the distinction between that exact equivalence of the Ising model in lattice gas to the approximate equivalence inherent in the notion of universality, which says that systems act in certain properties the same way. So universality says that close to the critical point, molecular details don't matter. This notion of exact equivalence, as we'll show in a sec, is a statement that irrespective of what external parameters I'm considering, these two models are exactly the same. Okay, so let's go ahead and show that, remind ourselves how we work through that calculation. So to map the lattice gas onto the Ising model, we recognize that the lattice gas has occupancy variables, 0 or 1. The Ising model have spin variables, plus or minus 1. So both can exist locally in one of two states. If we take a mapping between each of those two states, which is linear and unique, we could, for example, say that Si is equal to twice Ni minus 1. That means that for each Ni, I return a unique S, and that S maps to the existing S's of the Ising model. So if we rewrite the spin variables in terms of those occupation variables, I can now go through the different terms in the energy function of the Ising model and see how to write them in terms of the variables of the lattice gas. And as we did before, we note that the sum over all the spins in the Ising model, written in occupation variables, is twice the sum over the n's minus twice the total number of spins. The double sum over nearest neighbors and a product of spin I and spin j results in 4 times the occupation variables Ni and j minus 4 times a sum over Ni times a sum over j primed. That's how I could write that double sum that, if I don't have any constraints, overcounts by a factor of 2. That is the sum over the nearest neighbors of spin I, or occupancy variable I, of which there are z plus an additive constant for the minus 1 term, which just gives me plus in z over 2, the total number of terms in that restricted double sum. So simplifying this, putting these two pieces together, the energy function for the Ising model is nothing but minus 4j sum over Ni and j restricted to nearest neighbors, minus h times twice jz. Oops, sorry, that h is inside. Twice h minus twice jz, a sum over ni, plus a constant that has to do with these constants here. But a constant shift to the energy doesn't change any of the statistics, doesn't change any observables. So if we redefine 4J as epsilon and note that mu could be written as twice h minus jz, then that energy function is the identical factor in the argument of the exponential in the grand canonical partition function for our lattice gas, or the energy of the Ising model is equal to the energy of the lattice gas minus mu n up to a constant, and thus the partition function for the Ising model is proportional to the partition function of the lattice gas. So indeed, solving one solves the other by renaming variables. That is a useful exercise to go through, not because it very distinctly demonstrates that the models are the same. That's a useful bit of knowledge. But what it is really useful for is helping to elucidate the fact that the lattice gas has an underlying symmetry, which is kind of hard to see otherwise. So the Ising model has an up-down symmetry at h is equal to 0. The energy is equivalent, and thus the statistical weight is equivalent if I take all of the spins in whatever configuration they are and flip all of them to their opposite sign. And because the models are the same, this must mean that the lattice gas as well has an underlying Z2 group symmetry. In fact, we can see that through this mapping. We noted that the chemical potential is equal to twice H minus JZ. The symmetry line in the Ising model is along H is equal to 0. So along mu is equal to minus twice Jz, which is equal to minus epsilon Z by 2 through the equivalence of what J is. That is a symmetry line along which configurations of the lattice gas with some amount of filled and occupied sites is equivalent to inverting all of the filled sites to unoccupied sites and all the occupied unoccupied sites and all of the empty sites to filled sites. And we can demonstrate that in a couple lines. So if we take the argument of the exponential and the partition function, which is the energy less that mu times n. Along this line, that is epsilon z by 2 times the number of particles in the system. That's the mu n term, minus the energetic term, which is minus epsilon ni and j restricted to nearest neighbors. This term has to be rewritten in order to make that symmetry apparent. So if we rewrite it, so it's epsilon z by 2 sum over I in I. Well, first, if we note that ni is equal to ni squared, since ni is 0 or 1, if I square 0, I get 0. If I square 1, I get 1. So I can make that a square. I can also introduce a sum over j in the nearest neighbors of I times 1. So it's just a number of terms in that sum that I've just multiplied by. If I divide by the number of terms in that sum, which is z by 2, then I've just multiplied by 1 in a very complicated way. Rewriting the argument of the exponential, I now have minus epsilon I can pull out of everything. I have a sum over I and j restricted. I have now an ni squared from the chemical potential term. I have a minus ni in j from the interaction term. Written in this way, I and j are equivalent. This term can then be separated into half from ni and half from nj because they're the same number of terms in that sum. Pulling out 1/2 gives me epsilon by 2, restricted sum, and a square, ni minus nj, which indeed manifestly has a particle-hole symmetry. If I take ni to 1 minus ni for all I, so I flip all the filled sites to empty. So if ni is 1, they go to 0. I flip all the empty sites to filled. So if ni is 0, it now goes to 1. That energy is left invariant. Pictorially, we would say that along this symmetry line, the line at which filled and empty arrangements have equal weight, pictorially we can imagine that as, say, a lattice that looks like this. Those sites are filled. If we do this particle hole inversion, we now change the filled sites to empty and the empty sites to full. Those two have the same weight. Along this line of mu is equal to minus epsilon, if I have all sites full and all sites empty, those also would have the same weight. So indeed, this is along the same line that coexistence must be established at low enough temperature such that I can have broken symmetry. I will expect that the coexistence chemical potential, the chemical potential for which the liquid is equivalent to the gas, is going to be given exactly by this value, epsilon by 2, with a minus sign. Okay, so this is a consequence of the exact relationship between the lattice gas and the Ising model. So really from here on out, we will just focus on the Ising model where the symmetries are simpler, but keep in mind that anything we say about the Ising model is equivalently said for the lattice gas. Okay, so thinking about the Ising model, a natural question to ask is how could we go about trying to solve it? As we remarked last time, a complication that's going to make doing this difficult is to note that the probability of observing some arrangement of spins or equivalently occupation variables is proportional to this Boltzmann factor, or the Ising model would look something like this. And for any finite j, that probability does not factorize. It does not factorize because of this term here that depends on the product of Si and Sj. Which is a bit of a bummer. Indeed, one can see that very clearly by writing down the probability of observing, say, spin 1 in some specific state, which is just proportional to the energy of spin 1, which is beta j spin 1 times a sum over its neighbors. If all I had was the beta h term, that would be a non-interacting spin system. We can solve it and have done so previously. But here, the spin 1 manifestly depends on spin j. Spin j would depend on spin 1. So these are coupled relationships that are not going to be easy to disentangle. However, while this is indeed true, in one dimension there's a trick. So what would a one-dimensional Ising model look like, where we have some one-dimensional lattice? We have spins that could sit on sites of that lattice. Maybe they are up or down. Let's call that one spin I. That one's there for I plus 1, I plus 2, etc. In such a system, the energy takes a particularly simple form. At h is equal to 0, the energy minus j times a product over pairs, or a sum over products of pairs, sum over pairs, that's what I mean to say. That product is simply Si times Si plus 1, summed only over I. So if I was to look at the first few of those terms, that's S1, S2, plus S2, S3, etc. S1 times S2, well, S1 could be plus or minus 1, S2 can be plus or minus 1. That might seem like there's a number of different values that the product could have, but of course that product can only itself be plus or minus 1. So there is the same amount of information in the number of the product S1, S2 as there is in the individual spin variables themselves. There's two states that a spin can be in. There are two states that the bond between two states can be in, or the product of two spins. So indeed, that motivates a reconsideration of what the Ising model in one dimension is, which is a set of bond variables, call them BI, which are the product of two adjacent spins. The energy can be exactly rewritten as a sum over those variables. So a mapping exists between describing the system as a set of spins or describing the system as a set of bonds between spins. If there are n spins, there are n minus 1 bonds. So we lose a little information in going to a picture of bonds from a picture of spins. So we've got to restore that information somewhere. And a way to do that would be to note that all SIs contain the same information as a set of bond variables plus the state of one of the edge spins, say spin 1. So there exists a set of equations relating the BIs to products of SI plus SI times SI plus 1 with one remaining free parameter, which is the value of spin 1. Written in this way, we can now write the partition function in the canonical ensemble for the Ising model as a sum over spin 1 being plus or minus 1 times a set of bond variables, B1 being plus or minus 1, B2 being plus or minus 1, etc., up to Bn minus 1, because there are n minus 1 bond variables, each times this Boltzmann factor of something expressible as a sum over those bond variables. And that is super convenient because then that has the form that we know and love and know how to handle. That factorizes into a product of beta j b1 times beta j b2, etc. Each one of those Boltzmann factors I can associate with its own partial sum. Say for B1 being plus or minus 1, I have e to the beta j b1. I have the factor from b2. And n minus 1 factors thereof. That sum over S1 is the sum implicitly over 1, being plus or minus 1. Each one of these partial sums I can then evaluate. This one just gives me 2. This one gives me e to the beta j plus e to the minus beta j. The same thing with this one. Same thing with all of the other partial sums over spin variables. I could write this in a nice compact representation as twice a sum of exponentials with different signs in their arguments is the same thing as twice hyperbolic cosine of beta j. And I have n minus 1 factors of that. Now, if there are many spins along this chain, this is very close to twice hyperbolic cosine beta j to the n. So we've just solved the Ising model. In one dimension, we've really done it. And now I've motivated the Ising model as being something which is a simple model for a magnet, simple enough that we can make analytic progress in it, but complicated enough, having the same basic physics, that we hope to be able to tease out universal behavior of it. So one of the things we might try to compute in order to understand that universality would be something like the heat capacity. And we know how to compute the heat capacity. That is 1 over kBt squared, fluctuations in the energy. And the way to compute that from the partition function is 1 over kBt squared, the second derivative of the log of the partition function with respect to beta. Taking those derivatives give us 1 over kBt squared. I have an n in the exponent. When I take the log, that will come outside. Taking derivatives with respect to beta pulls out a factor of j. And then I have a derivative of the derivative of minus, 2 minus signs, minus minus. The derivative, first derivative of hyperbolic cosine with respect to beta j would give me a hyperbolic tangent. The second derivative gives me another factor of j, so I have 1 over kBt squared. If I divide through by n, j squared. The derivative of hyperbolic tangent with respect to, oh, I said beta h, I meant beta j. The derivative of hyperbolic tangent with respect to a variable in its argument is 1 minus hyperbolic tangent squared. So we've computed the heat capacity. Drum roll, please. If we were to plot that as a function of temperature, what do we see? Well, very low values, hyperbolic tangent squared is 1. 1 minus 1 is 0, so it starts 0. At very large values of its argument, hyperbolic tangent is 1. Square it is still 1. 1 minus 1 is also 0. So it starts, it ends very close to 0, and in the middle, it increases. but it does not diverge. Indeed, there's no place in this equation that is singular. So this certainly looks like our Ising model is not the model we were hoping for. Not the model that we can use to uncover the rules of broken symmetry, the ideas of universality. So, two things could be going wrong. One might be that the model's insufficient. We need to gussy it up, add some bells and whistles. Two, that our calculation is somehow flawed. We've done some kind of fast and loose things with moving to this bond variable to do the calculation, setting everything, setting h to 0 to begin with. One should maybe do the calculation a little more carefully. So before we give up hope on our Ising model, let's do that. So to really show that the Ising model does not break symmetry, to really show, we need to do something more carefully. We would need to compute the partition function with finite h. We've only worked at 0h. Maybe there's a subtlety with how you take that h goes to 0 limit. To exclude the spontaneous symmetry breaking, we would need to compute explicitly the magnetization, which we could do by taking the derivative of log q with respect to beta h. Having a finite h will allow us to do that. Dividing by n gives us a means of doing it. We have noted previously that a singularity only exists in the thermodynamic limit, so we would need to take that thermodynamic limit and only then set the field to 0 and show that as we did it, the expectation value of m goes to 0 as opposed to remaining finite. So there's a much more rigorous calculation required to really demonstrate that there is no symmetry breaking. So we're going to do that. I'm going to spend the remainder of the lecture going through a way of tackling one-dimensional problems, which is fairly general, and will let us demonstrate whether or not the Ising model really does break symmetry or not. Okay, so those are the steps. Let's go. So step 1. Let's consider, for concreteness, an Ising model on a ring. So we have spins periodically arranged on a line that intersects itself. On such a ring, the partition function is a sum over spin 1 being plus or minus 1 up to spin n being plus or minus 1. We have the argument of those Boltzmann factors, because it's still a line, it does have this form of the interaction being a sum of products in I or Si times Si plus 1. And we need to do this at finite h. Okay, so that's the form of our partition function. So now let's think, what does this look like? So if we actually were to write out what some of those terms were, so we'd have one term which was beta j, let's do h, we'd have beta h s1 plus beta j s1 s2. I could try to look at the next term, that would be beta h s2, beta j s2 s3. That doesn't look very symmetric. If I wrote the field term like so, so split each spin variable in half such that each subsequent line symmetrizes the role of each spin variable. So again, these are products of terms. If I kept going, I would get all the way up to e to the beta h s n by 2 plus beta j. It's on a lattice, on a ring, so S1 is connected to Sn. And here's the last little bit of the S1 term, from which I borrowed some from that term up there. Now this has a particularly appealing form. Each term looks like the next, just re-indexed. And each term in the parentheses has two dependent quantities. This term depends on the value of Sn and the value of S1, for example. So let's define a function t that depends on those variables, S1 and Sn for that row. Here would be t of S1 and S2 for that row. That means that that whole Boltzmann factor can be written as a product of these t functions. So Q being a sum over S1 plus or minus 1 up to Sn plus or minus 1. Let's use our compact notation of the set of spin variables. And the argument of that sum is this product of t variables S1, S2 times t of S2, S3, all the way up to t of Sn, S1. Now, mind you, the sum outside of that product is a sum over all of those spin variables, S2, S3, Sn. Now, that has a form that some of you might have seen before. That's the form of a matrix product. Namely, if I had a matrix A times a matrix B, and I looked at the ith, jth element of that matrix, I could write that down as a sum over an intermediate index k AIK times BKJ. So a matrix product, the ith element of a matrix product, can always be written down as a sum over an intermediate index, where that intermediate index plays the role of the column of the first matrix and the row of the second. So that means that partition function is just one big matrix product. So let's define this T matrix as this T function for spins 1, 1, spins 1, minus 1, spins minus 1, 1, and spins minus 1, minus 1. So those are the different values that the pair of spins, which T is a function of, can take. Each spin can be plus or minus 1, so there are 4 possibilities. So this is what is known as a transfer matrix. This is abundantly a representation of the partition function, because if I note S2 times this T function S1, S2 times the T function S2, S3 is the Si, S1, 3 index of the product of these two transfer matrices. That realization lets us then write Q as a sum over the outside indices, which in this case are 1 and 1. So that's a sum over S1, that transfer matrix, to the nth power, the S1, S1 element. That is nothing other than the trace over this transfer matrix to the n. That doesn't necessarily look like it's made our lives any simpler. Taking a matrix to the nth power looks forbidding. And indeed, taking n factors of some matrix in general is a very complicated thing to do. However, this transfer matrix is a 2 by 2 matrix. We can diagonalize 2 by 2 matrices, in which case taking the nth power is just taking the nth power of each individual eigenvalue of that matrix. So written in a basis that diagonalizes T, we would have some eigenvalue lambda plus, some other eigenvalue lambda minus. Raised to the n, that is just n factors of lambda plus and n factors of lambda minus. A trace would then just be the sum over those two. However, if n is arbitrarily large, only the dominant eigenvalue is going to be important. So if we take some number that is larger than some other number, raise each of those numbers to a very large power, only the one which is the largest or the dominant one will be non-vanishing. So this is an interesting observation. A partition function can be thought of as a eigenvalue problem, where in the thermodynamic limit, all we worry about is the dominant eigenvalue of that transfer matrix. A useful mathematical realization for one-dimensional systems, not necessarily all that useful for general systems, unfortunately, because it can be quite difficult to construct and diagonalize that general system. All right, so let's go ahead and diagonalize this transfer matrix. So it has the form of A, B on the off diagonals and some different number C on the diagonals. This is specifically e to the beta H plus beta J, e to the minus beta J, e to the minus beta J, and e to the minus beta H plus beta J. Again, for 1, 1, 1 minus 1, minus 1, 1, and minus 1, minus 1. So a 2 by 2 matrix has two eigenvalues, lambda plus and minus, which are given by the determinants of the, or it's given by the roots of the polynomial associated with that matrix, which are 1/2 A plus or minus, characteristic roots are 4b squared plus A minus C, quantity squared. Or in our specific case, lambda plus or minus is equal to e to the beta J times hyperbolic cosine beta H plus or minus hyperbolic sine squared of beta H plus e to the minus 4 beta J. Again, when we raise to the n, only the dominant eigenvalue is important. That is the eigenvalue associated with the positive root, or the plus, the strictly positive quantity inside the root. And so the free energy, or minus kBt, the log of the partition function, is given by n with a minus sign times J plus kBt log of hyperbolic cosine beta H plus hyperbolic sine squared beta H plus e to the minus 4 beta J square root of inside those brackets. So we've just computed exactly n for finite h, the partition function, and associated free energy. So we are now in a position to move on to step 2, which is to find the average magnetization per spin and to eventually take the thermodynamic limit of that quantity. So what do we get? So the derivative of log of Q with respect to beta H is a way we can do it. So M by N is d log Q d beta H with a minus N divided by N. That is equal to something really nasty. Let's see, what's simple? So the H dependence is not in the first term, so that will go away. It's all in the second term. And there's 2 factors from the hyperbolic cosine and the hyperbolic sine squared. So we should get 2 terms. So first, taking the derivative of the log is going to bring down a factor of this whole thing. That's from the log. Now the derivative in sine, derivative of hyperbolic cosine is hyperbolic sine. The derivative of the square root of hyperbolic sine squared plus that constant is going to give us, so derivative of hyperbolic sine squared is sine times its derivative, hyperbolic cosine. Then I pull down the square root, giving me back sine squared plus this factor all in the square root. Whew, isn't that ugly? But note that it is independent of n, so that makes that part of our life very simple. We can trivially take the large n limit. So at least that part of the calculation is straightforward. All right, now we need to take, so what was step 4? Step 4 told us to take the limit of h going to 0, and we should be able to show that m goes to 0 if it does not break symmetry. It would go to something finite if it did. All right. So to think about how to take the limit of this really nasty thing, let's think about how the functional dependence of these 2 quantities, hyperbolic sine and hyperbolic cosine, depend on their arguments. So as h goes to 0 plus epsilon, how does hyperbolic cosine function? It would go to 1. Hyperbolic sine would go to 0. Both of those are true if beta is finite. If beta is not finite, something different would happen. Well, let's think about beta being finite first. So cosh goes to 1. All that matters is that both of these, so let's maybe for completeness rewrite this average magnetization. We have a sinh beta H plus a beta H cosh beta H all over, what are those factors? Cosh plus that, that's right. Okay, that's the average magnetization, really ugly. However, both of those are proportional to sinh, which is going to 0. So M will go to 0 as H goes to 0 and T is not equal to 0. What happens if T is equal to 0? So if T is equal to 0 and we take the limit of H going to 0, M will go to something finite. That's a singular perturbation, harder to see directly, but not too difficult to demonstrate. So in fact, there is a symmetry breaking but it's kind of a trivial symmetry breaking. It only occurs at 0 temperature, where there are, in fact, 2 degenerate ground states. So if I start in one of them, I will be stuck in it. If I start in the other, I'll be stuck in that one. And having epsilon in the field will with infinite sensitivity set which one of those ground states is the preferred one. However, at any finite temperature, the one-dimensional Ising model does not have a spontaneous symmetry breaking. It does not exhibit a critical transition. So indeed, this model in dimension does not exhibit a phase transition. There are no critical fluctuations, no way of teasing out a critical exponent. So what happened to this notion of universality? Do some molecular details matter and not others? Do we need to gussy up the model and add additional terms? As was already alluded to in the live session, we will see next lecture that there is a molecular feature that matters, but it's a pretty generic one. It's the dimensionality with which a system resides in, the thermodynamic dimensionality, the dimensions, the number of directions that I can take the system infinitely large, for which I can take the thermodynamic limit. So in fact, we will see that one dimension is special. 2 dimensions already will fix this problem. To just give you a prelude of why one dimension is special, I want you to think about what would happen if I took a system that was all up, so in a symmetry broken state, and I introduced the lowest energy excitation that results in zero magnetization. That lowest energy excitation would introduce one defect, which separates domains of spin up from spin down. If there were equal amounts, that would mean that the magnetization now is zero. Now think about the thermodynamics of that defect. What are the associated energetics? What does the system, what is the thermal fluctuation that has to happen in order to generate that defect? And what are the associated entropic contributions to that free energy? How many ways can I put down that defect? Landau was the originator, Lev Landau, famous theoretical physicist, was the originator of this argument. It's a very powerful one. You should be able to convince yourself, and we'll work through this next time, that this single excitation that destroys long-range order, that destroys the net magnetization of the system, is something that in the thermodynamic limit actually becomes overwhelmingly favorable at any finite temperature. If you can understand that, if you can work out those energetics, you can then be able to convince yourself that if you just go to 2 dimensions and try to do the same thing, something fundamentally different happens. Okay. Well, that's all I wanted to say for today. So to recap, we've introduced a couple technical tricks to study one-dimensional systems, the so-called transfer matrix solution of the Ising model, which gave us a way of computing the partition function exactly for this interacting system, because it could essentially be mapped onto a non-interacting system. Not surprisingly, therefore, this system did not exhibit a phase transition. There's some hope, as I've suggested, if we pay closer attention to the dimensionality of the space, this notion of universality will be reestablished. We'll save the day. The model is simple enough, though also complicated enough, to exhibit universal behaviors. Those we will try to start approaching with a little more finesse and through a little more, slightly more approximate means in the next lectures. All right. Everyone take care and stay safe, and I'll look forward to seeing you all in the live session.